Here at Michigan State University, we have an active diabetes research group, and today we will be talking to you about diabetic retinopathy research that we do.
We are a multidisciplinary facility supported by numerous colleges and departments within the university to really facilitate investigators who are interested in learning more about the molecular mechanisms of disease.
Diabetic retinopathy is a result of the diabetic insult on the retina. It affects all the retinal cells. Clinically, it's mainly vascular disease. Diabetes affects vasculature in the retina and it becomes leaky, breaks down, and then new vessels, very unstable blood vessels, start growing, and all of that happens in the front of the field of view. Because of that, the patient can lose vision due to diabetic retinopathy.
So at MSU, the research focus is on how hyperglycemia induces chronic inflammation in the retinal tissue. And we primarily focus on retinal Müller cells, which are the primary glia of the retina. And we kind of think about Müller cells as the gatekeeper for neuronal and vascular functions. So when Müller cells experience a hyperglycemic insult, they predominantly produce interleukin-1 beta as the first response. This interleukin-1 beta then comes back and activates the cells even further, making even more interleukin-1 beta, which we have identified as autoinflammatory events. So we actually think that the chronic inflammation is initiated by hyperglycemia but maintained by the lipids. Once this autoinflammatory event is set in, you get increased and amplifying of inflammation that then can reach other cell types like microglia or the vasculature or a neuron, and they will recruit bone marrow derived cells into the retina, and therefore the inflammation that is initiated in the Müller cells spreads throughout the retina, affecting other retinal cell types, causing a chronic state of inflammation in the diabetic retina.
For the last 15 years, Dr. Busick and I have been collaborating on the role of vascular progenitor cells in the management or pathogenesis of diabetic retinopathy. And more recently, we've been collaborating with Dr. Moore's laboratory, focusing on the role of inflammation, and particularly the bone marrow cells and their role in propagating diabetic retinopathy. The bone marrow is a very interesting tissue. About 1 million cells are released every second into the peripheral blood. In diabetes, these circulating cells tend to be like little tennis balls. They're very hard, and then they don't leave the vasculature. They don't go into the reparative cells. Don't go into the retina. They're not able to migrate properly. They can't even get out of the bone marrow. So what we've been able to study with Julia's lab and with her collaborators here at MSU is why are the cells rigid? And can we fix them to make them migrate better? Because migration is one of the critical features of these cells. They have to migrate out of the bone marrow. They have to migrate into the tissues to repair. So the bone marrow produces vascular reparative cells as well as inflammatory cells that are involved in managing infection. However, in diabetes, this is imbalanced. There's too few of the reparative cells and too many of the pro-inflammatory cells. This ends up resulting in the fact that the good cells do not get out into the circulation where they can facilitate vascular repair. However, because the bone marrow makes too many of these pro-inflammatory cells, they're still released in higher amounts than normal because there's more of them being produced, and these can propagate the adverse or pathological changes in the retina.
When we were doing our research in the retina, we realized that retina has very specific lipid profile. And as we were looking at it, we also realized that retina has its own lipid metabolism. All the enzymes of producing lipids were very highly expressed in the retina, even higher than in the liver, which was very unexpected. You don't expect retina to be a fat-producing tissue. It's not associated with fat when you speak about the retina, but we did find that a lot of lipid metabolic enzymes have high expression in the retina than even in the liver, which is your typical lipid-producing organ.
My role in the development of sensitive ESI-MS methods for lipid analysis included enhanced sample preparation strategies to allow us to pull out a wider variety of lipid metabolites from the cells or tissues that we're studying. Second, I was involved in developing workflows that really take advantage of the latest generation of high-resolution, accurate mass, Orbitrap-based mass spectrometry platforms. We can now analyze a wider variety of lipids simultaneously to really understand the diversity of the lipid environment.
We are already developing several therapeutic approaches, looking at the lipid as a treatment modalities. We are looking at the ways to increase the amount of these very long chain lipids that are stabilizing. At the same time, we are looking for the inhibitors and ways to reduce the amount of short chain lipids and ceramides in the retina.
The future of mass spectrometry-based lipidomics research is that as mass spectrometry platforms continue to evolve, detection limits will be further pushed back. This will enable us to analyze a greater number of biological molecules simultaneously, enabling true multi-omic experiments.